Yeah, this is Math 111 OLC, Unit 3. We're going to start Chapter 3 today in Section 3.2, which is entitled Solving 2 by 2 Systems Algebraically. And this is winter session 2012. Alright, goal. What is our goal in Section 3.2? Basically, we'll be given two linear equations, or line equations if you will. And let me just throw one out here for example. Alright, if necessary, I could graph the line equation for both of these lines. What I want to do is solve simultaneously. Solve this, I'll call it a 2 by 2 system. When I say 2 by 2, I'm meaning two equations with two unknown values. So we're not just solving for x, we're solving for x and y simultaneously in two different equations. Alright, if I look at this equation, I can, using techniques of Chapter 2, I can graph that line that represents the solution set of that equation. I could also graph this line that determines the solution set for that equation. And of course, there's infinitely many solutions to either of those equations, but when I consider them both individually, I think you can easily agree if I'm looking for a simultaneous solution of two different lines, the common solution, the simultaneous solution to both, will be a point. So basically we're looking for a point in the xy plane that will solve both these equations simultaneously in section 2.2. So let me write that down. The solution set for both this system, for both equations in the system, is a single point of intersection of those two lines. Now, in section 3.1, which we're going to pretty much bypass, they talk about solving things graphically. But as you might guess, even with the most highly resoluted graph paper, and even with the best hand techniques in graphing lines, you may not be able to identify a solution point very specifically. Basically, graphs are kind of sometimes a hit and miss kind of thing, especially if your solution coordinates turn into fractions. Right? So let me write that down. Graphical solutions. Yeah, I'll just say they're not very accurate. Or they may not be accurate. They are not reliably accurate, let me put it that way. Not very accurate, especially if the coordinates of the solution lead you to fractional coordinates. Alright, especially if you've got fractional coordinates. Alright, what are we going to do? Well, we're going to largely bypass the idea of solving graphically, and we're going to determine really two methods to solve systems algebraically. And with pen and pencil techniques, algebraic, hang on a minute, I spelled it wrong. Algebraically. Okay? Basically, we're going to have two systems, or two techniques to solve these systems, I should say. We're going to solve, one method the book talks about is substitution. The first one they talk about is substitution, and the next technique they talk about is solve by elimination. And they're both okay. I suppose, depending on the problem, one might be a more preferred technique of solution than the other. It depends on the problem. Alright, let's do one by substitution. Here is that original system I wrote on the screen above. Alright, what I'm going to do is solve this system simultaneously by substitution. Remember, you want to solve both of these line equations at the same time. Find the point, the x-coordinate and the y-coordinate, that solves both at the same time. What do I mean by substitution? What do I mean when I say solve by substitution? Alright, if I look at this first equation, x plus 2y equals 4, you can see I can easily solve for x in terms of y using the first equation. Alright, if I take the first equation and solve for x, then I can take this expression for x in terms of y, substitute it into the other equation for my x variable. And if I do that, I will then result in one equation with one unknown, and I can solve for y very easily. Well, let me go ahead and grind that out. Get 8 minus 4y minus y equals 3. 8 minus 5y equals 3. If I subtract 8 from both sides, I get minus 5y equals minus 5. And I get a y value equal to 1. Alright, this tells me, let me circle this, this tells me the y-coordinate of the point of solution to both of those equations in that system is 1. So I know that my solution point is going to look like this. Y has to be 1. But I don't know what the x-coordinate is. Well, what I can do then is go to either of these equations, since my point of solution has to solve both, plug in the y value of 1, and solve for x rather easily. I'm going to pick the first equation, x plus 2y equals 4, and sub in y equals 1. So x plus 2 times 1 equals 4. And of course x plus 2 equals 4, so that means x is going to be 2. So I have now determined the point of solution for both those equations in the system simultaneously. So my solution point is the point x equals 2 and y equals 1. Alright, so that is the substitution method. There is also an elimination method. It's a different road, but it gets you to the same point. Let me show you what I mean by the elimination method. I'll start out with the same equation, or the same system of two equations. So my solution should be the same, no matter what technique I use. Alright, what I'm going to do is doing algebra type things to one or the other equation. I'm going to rig it so that when I add these two equations, one of the variables will be eliminated. Let me show you what I mean. There's the system I want to solve. Let me write that down. This is the command usually issued: solve or solve the following system. I notice if I multiply the second equation by 2, and I will get a cancellation of the y variable if I add those two equations. So what I'm going to do I'm going to take, you know what I'm going to do? I'm going to label these equations 1 and 2. And what I'm going to do is I'm going to leave the first equation alone, and in the second equation I'm going to multiply it by positive 2. So I'll illustrate that with these symbols. These symbols, I'll say 2 times equation 2 results in 4x minus 2y equals 6. It's the same system. It has the same solution set. I've done algebra type things to both sides of the equation in that second equation, so I will not affect the solution set. Basically what I've done is tailor things so that when I add these two equations, I'll get a cancellation of the y variables. Alright, so the plus 2y and minus 2y cancel out. I'm left with 5x equals 10, and of course x equals 2, which should look familiar. That's the solution I got for x using my substitution method as above. And again, if x is 2, well, I know my solution, my point of solution to both these equations has to look like this, 2 comma question mark, but I don't know why. And again, I can pick either of these equations to solve for y once I know that x is 2. I'm going to pick the first one again. I'll plug x equals 2 into the first equation. Alright, so 2 plus 2y equals 4, 2y equals 2, and of course y equals 1. So when x is 2, y is 1, and I can symbolize my answer, my point of solution, my solution to the 2 by 2 system is going to be the point x equals 2, y equals 1, or in coordinate fashion, I'll put it in ordered pair 2 comma 1. Alright, so that's the elimination method. And I get the same solution I got with the substitution method. Let me point that out. 2 comma 1 with substitution, 2 comma 1 with elimination. So which you want to use, which technique you want to use, I suppose is up to you. The book often specifies a particular solution. On test day I probably won't, and leave it up to you to decide. And it depends on the problem, I suppose. Often there's no glaring advantage to one or the other. I suppose in some situation one might be a more preferable method of attack. Let's try another one. Solve. Another 2 by 2 system. 2 equations with 2 unknowns. 3x minus 4y equals 9. X plus 2y equals 8. Alright, both these equations are in standard form. Remember, standard form of a line equation is ax plus by equals c. Basically, I've got a multiple of x plus a multiple of y equaling some constants. Now, not all line equations, as you know, are in standard form, but at least the first few ones here are. Alright, I'm going to solve by elimination. I'm going to solve this system by elimination because I know that when I multiply the bottom equation by 2, I'm going to get a cancellation of the y variables, much like in the problem above. Alright, so what I'm going to do, I'm going to leave the first equation alone, and I'm going to multiply the bottom equation through by positive 2. So I get 2x plus 4y equals 10. Alright, I think we see why we multiplied the second one by positive 2, because then when we add these two equations, I get a elimination of the y variable. So I get 5x equals, oh, hang on a minute, equals 2x plus 4y. I made a mistake here. Please correct your notes. If I'm going to multiply the bottom equation by 2, I get 2x plus 4y equals 16. 2 times 8 is 16. Where I got a 10 from, I'm not sure. Alright, so please make that correction and we'll go on. So I get 5x equals, again the y variables cancel out, equals 25. That of course means x equals 5. So again, my solution to this system is going to look something like this. When x is 5, what is y? Well, I can solve for y very easily. Just go to any of these equations and plug in x equals 5. I'm going to use x plus 2y equals 8. Grab this equation from the original system, plug in x equals 5. So 5 plus 2y equals 8. I'm going to subtract 5 from both sides. I get 2y equals 3. And of course then y equals 3 halves. And sometimes your coordinates will be fractional, which is why we don't always rely on graphical solutions, not very often anyway. So when x is 5, y is 3 halves. There is my solution set, my point of solution to the given 2 by 2 system. Okay? Alright. Let's talk about, do another one of these. Let me get a fresh screen here. Let me make a note here. If you got a 2 by 2 system, namely 2 equations with 2 unknowns, please note that systems of equations are not always in the form ax plus by equals c. In other words, they're not always in standard form. Let's look at this equation I'm going to ask you to solve. I grabbed this one out of the book. Let's see, I've got 4 times x minus 2 equals minus 9y, and 2 times x minus 3y equals minus 3. Alright, on test day we'll be asked to solve a similar system to this. And what am I going to do? Well, do I use the elimination method or do I use the substitution method? What I would do is first convert to standard form. Things are cloudy. The direction I want to take is somewhat vague because it's not in standard form and I can't really discern which way is the best way. Alright, what I'll do is take this first equation. Again, I'm going to not change the solution set at all of this system, but basically juggle things around algebraically. I'll get 4x minus 8 equals minus 9y if I perform the indicated multiplication in equation 1. Downstairs, I get 2x minus 6y equals minus 3. And what I'll do, I'm almost there. I'm almost in standard form. I'm going to add 9y to both sides and add 8 to both sides to get that first equation in standard form. Now watch me here. It's so easy to make a mistake. I get 4x plus 9y equals 8, and 2x, let's see, 2x minus 6y equals minus 3. Alright. What am I going to do? Are we going to use a substitution method or an elimination method? I'm going to pick elimination. If I try to solve for one variable in terms of another here, I'm going to get some cumbersome fractions. And I think I see here that 4x and 2x, I can easily rig things so I can eliminate the x variables very easily. Alright, I'm going to leave the first equation alone. Let me rewrite it. 4x plus 9y equals 8. And I'm going to take that second equation and I'm going to multiply that by a negative 2. Equals positive 6, right? Alright, so multiply this equation through by negative 2. Let me check it. Minus 4x plus 12y, and minus 2 times minus 3 is positive 6. Alright, I've now rigged this system so that when I add these equations, I'll get another equation, and I get the resulting equation, 21y equals 14. And if I divide both sides by 21, I get y equals 14 over 21, which reduces to 2/3. So I know my solution, my point of solution for that system of two line equations is going to look like this. The y-coordinate has to be 2/3. Alright, and I can pick any of the above equations and plug in 2/3 for y. And I'm going to pick this one here, 2x minus 6y equals minus 3. I'm going to plug in y equals 2/3. 2x, whoops, too close there. Let me fix this up here. Okay, so 2x minus 6y equals minus 3. Again, it really doesn't matter which equation you pick. As long as you know what y is, you can solve for x using any of the equations used. So 2x minus 6 times 2/3 is minus 3. Alright, so I can solve for x now. Well, 6 times 2/3 is 4, so I get 2x minus 4 equals minus 3. So 2x equals 1, adding 4 to both sides, and x equals 1/2. Alright, so I know when when y is 2/3, x has to be 1/2. So I can summarize my point of solution. This is the solution set to the system. X equals 1/2 and y equals 2/3. Okay? Let's see. Let's try another one. Now, some of these get a little nastier, as you might expect. Solve. 2/3 x minus 1/4 y equals minus 8, and 1/2 x minus 3/8 y equals minus 9. Well, this is a little nastier, and these two linear equations are both in standard form, but pretty much all these coefficients of x and y are fractions, kind of unpleasant fractions. Well, what are we going to do? Well, probably the first thing I would do here is to clear the fractions. And I can do that by multiplying both sides of the respective equations by the LCM, the least common multiple of all those denominators. So what I'm going to do is, in this first equation, I'm going to multiply everything by 12. So I'll denote that with 12 times equation 1. And that will result in an equivalent equation with the fractions gone, right? This whole number of coordinates. Alright, so I'll say 12 times 2/3 x, 3 cross cancels into 12 4 times 2x is 8x, minus 4 cross cancels into 12 3 times minus 1y is minus 3y, equals minus 8 times 12 is minus 96. Okay? Alright, so that first equation reduces to 8x minus 3y equals minus 96. Alright, and I'm going to use that equation in that form in a minute. The bottom equation, number 2, I'm going to multiply both sides by 8. Right? 8 is the LCM of all denominators in that second equation. Alright, so I'll write that down. 8 times 1/2 x minus 3/8 y equals minus 9 times 8, multiplying both sides of that second equation by positive 8, and I'll get 4x minus 3y equals minus 72. Alright, so I've got now equivalent equations with no fractions. Let me rewrite those. 8x minus 3y equals minus 96, and 4x minus 3y equals minus 72. So I've got an equivalent system, the same system, same solution set, without any fractions bogging us down here. Alright, so, well, what are we going to do? I'm going to take this first equation and multiply by negative 1. Alright, because then I see when I add that to my second equation, the y variables will eliminate, and I'll get minus 4x equals, and 96 minus 72 is positive 24. And when I divide both sides by minus 4, I get x equals minus 6. Again, so my point of solution for both the original equations is going to have an x-coordinate of minus 6. And I can take any equation I like and plug in x equals minus 6. I'm going to use this one here. Now that I know x has to be minus 6, I can say 4 times minus 6 minus 3y equals, that's an equal sign, minus 72. So minus 24 minus 3y equals minus 72. So minus 3y equals, well, what's minus 72 plus 24? It's going to be a negative 48. And I'll divide both sides by negative 3. And I get a positive 16. So I know when x equals minus 6 in this system of two-line equations, y has to be positive 16. So my solution set for this system is the point minus 6, comma 16. Okay? Alright. A couple more types I want to talk about before we call it a day in this section anyway. Let me go ahead and get a new layer. Alright. Let's say I want you to solve the following system. And instead of x's and y's, I'm going to designate the variables as a's and b's. Alright, well, the good news is these two equations in our system are in standard form, but one of them involves decimals and the other one involves fractions. So what I'm going to do is multiply the first equation by 10, and all these decimals will turn into whole number coefficients. Similarly, if I take the second equation and multiply through by the LCM of all these denominators, that's 3, all these fractions will go away. Alright, so I'm going to say 10 times equation 1 will result in this equation, equivalent equation, 3a plus 5b equals 5. Looks better already. The bottom equation I'm going to multiply by 3 to make these fractions go away, and then end up with 4a plus b equals 9. Right? Alright, this is an equivalent system to the original system, just with more convenient multipliers and coefficients. Alright, maybe I can do some work in my head here. If I take this, well, let's see. Now the last couple ones we did with elimination method. Let's try this one with a substitution method. Well, I can easily solve this first equation for b. B in terms of a. So 3a plus b equals 5, so that means b equals 5 minus 3a, and I can substitute then that expression for b in the other equation. Well, that will result in this equation, 4a plus 5 minus 3a equals 9. And now we've got one equation with one variable that I should be able to solve pretty easily. 4a minus 3a is 1a. If I subtract 5 from both sides, 9 minus 5 is 4. So I know that my point of solution is going to be 4, comma, whatever b turns out to be. And again, you can use any of the above equations to solve for b. I might as well pick this one here. I know that a is 4. And 4 times 4 plus b then must equal 9. And 4 times 4 is 16. So b is going to be 9 minus 16, and that's minus 7. So when a is 4, b is minus 7, and that is the point of solution for the 2x2 system I was given. Alright, one more item I want to talk about. I call these next types double surgery. Let me give an example that I'm talking about. This is number 32 in the homework list on page 245. Give me a minute to write this down. 2x plus 3y equals 31, and 3x plus 2y equals 39. If I am asked to solve this system, well, if I try the substitution method, I'm going to end up with some cumbersome fractions here. No way around it if I use the substitution method. But if I then try the elimination method, I'll notice that 3 is not a multiple of 2, and similarly, in the y slot, 2 is not a multiple of 3. So I'm going to have to perform, if I want to use the elimination method, I'm going to have to do what I call double surgery. I'm going to have to multiply both equations by something to get a convenient cancellation of one variable or the other. I'm going to take the first equation and multiply it by minus 3. I will then get minus 6x minus 9y equals minus 93. Okay? Alright, what I'm going to go for here is elimination of the x variable. If I then multiply the bottom equation by 2, I'll symbolize it like that. 2 times 3x gives me positive 6x plus 4y equals 78. And I think with that double surgery, we can then easily see the x variables are going to eliminate when I add these two equations. I get minus 5y. Again, the x columns cancels out. Minus 5y equals 78, 88. That's going to be negative 15. And of course, dividing both sides by minus 5, I get y equals positive 3. Alright, so my point of solution is going to look like this. When y is 3, well, we still have to determine what x is to get that second coordinate. And again, I can use any point or any equation in the above list. I'm going to pick this very first equation, 2x plus 3y equals 31. Recall, this point must solve both equations. So you can use any one you want. Alright, so when y is 3, I get 2x plus 9 equals 33. Equals 31, sorry. 2x plus 9 equals 31. I'm going to subtract 9 from both sides, and 31 minus 9 is 22. And of course I get a solution for x of x equals 11. Alright, so when y is 3, x has to be 11. That is the point of solution to both equations in our system simultaneously. So I'll summarize that. When x is 11, y is 3. So this is the point of solution of my 2 by 2 system. Alright, I'm going to stop here. Again, homework problems are assigned as usual, and this concludes section 3.2 in Unit 3, solving 2 by 2 systems of equations algebraically.